Okay, so welcome again. This is the continuation of the previous lecture. We started discussing language model, right? Last class we discussed Ingram language model, right? Specifically bigram language model. We focused on bigram language model, and we looked at how we compute bigram language model. Basically, in any bigram language model, what we do, we compute two counts, right? The count of the bigram, which is wi minus 1 wi, and the count of the unigram, right? Wi minus 1, right? And we also discussed, we also observed that in a normal bigram kind of language model, what we do, we first compute a bigram matrix, right? Which consists of unigram, cross unigram kind of rows are unigrams and columns are also unigrams, right? Rows are essentially vocabulary words, columns are also vocabulary words, right? And every entry in that matrix indicates the bigram count, right? We also observed that although the matrix is asymmetric, but the sum of rows for a particular entry and the sum of columns of a particular entry is the same. Okay. We also discussed smoothing techniques. We started with a simple add-1 smoothing, right? Where we basically blindly added 1 to all the entries of the bigram matrix, right? And when we add +1 to all the entries, right? What does it mean? What does it mean? Let's say the earlier count was 2, now the count is 3. Earlier count was 0, now the count is 1. What does it mean? It basically means that I have encountered that bigram one additional time, right, than the count that I had earlier. Okay. And we also observed that because of this, when we add +1 to the numerator, we had to add plus mod v, right, to the denominator. And what is this mod v? Mod v is the size of the vocabulary, right? And this was needed because essentially this is a conditional probability, and we have to make sure that the sum of this conditional probability should be 1. And we also discussed that this kind of smoothing techniques have some problems, because what happened is that those counts which are very high, right, those counts will become very, very low. Let's say 600 will become 300, right? 500 will become 100, and so on and so forth. I mentioned also in the last class that this is essentially about stealing money from the rich and distribute it to the poor. So today we will discuss two advanced smoothing techniques, right, which will address the problems that we had earlier in advanced smoothing, right? Add K smoothing, Laplace smoothing. All right, so advanced smoothing algorithms, and we will look at two algorithms today: Good-Turing and Kneser-Ney or Kneser-Ney, right? Some people pronounce it as Kneser-Ney, some people pronounce it as Kneser-Ney. Okay, so what is the intuition here? The intuition is we use the count of things we have seen once to estimate the count of things we have never seen. Okay, this is the intuition. Let's look at it with an example. We define a concept of frequency of frequencies, right? What is a frequency of frequency? NC, we denote this by NC. NC is the frequency of frequency C, right? Let's assume that this is our corpus, right? Rohan, I am Rohan, I like to play. How many times the word I appears? The token I appears 3 times, Rohan 2 times, am 2 times, like 1 times, and so on and so forth, right? So what is N1? Frequency of 1, frequency of count 1 here. What is N1 here? 3. What is N2 here? 2. Frequency of count 2. What is N3 here? 1. Right? Frequency of frequencies. Okay. Now, what Good-Turing smoothing intuition? What is the intuition behind Good-Turing smoothing technique? The intuition is that we look at the count of 1, right? Count of count 1 to estimate the count of 2. right? Let's see. So let's assume that you are bird watching in let's say Jim Corbett National Park, and these are the birds that you have already observed, right? 10 flamingos, 2 kingfisher, 1 Indian roller, woodpecker, peacock, and so on and so forth, right? There are 18 birds that you have observed so far, right? So if I ask you what is the probability that the next bird that you are going to see is woodpecker, what is the probability? 1 by 18, right? And this is maximum likelihood estimate. What is maximum likelihood estimate? Maximum likelihood estimate says that the best probability that you can derive from the observation, and the best probability is 1 by 18 here for woodpecker, right? So maximum likelihood estimate for woodpecker is 1 by 18. If I ask you what is the probability that the next bird that you are going to observe is purple heron, say for example, a new species altogether, according to the maximal likelihood estimate, this would be 0 by 18, right? But what Good-Turing will say, the Good-Turing estimate will say that in order to estimate the count of 0, I will look at the count of 1, right? So how many count 1 is there? What is n1? 3, right? So to estimate this, I will use n1, right? And based on that, I will measure the probability. So this will be n1 by total birds, 18. So 3 by 18. Okay. So in order to measure the cases where the actual count is 0, I will look at the count of 1 and then measure the probability. So if this is 3 by 18, if I ask you again the same question, what is the probability that the next bird is going to be woodpecker, what is the count? Would that still be 1 by 18? Would that still be 1 by 18? It is not. Why it is not? Because we already subtracted, we already took some probability mass from 1 by 18 in order to compute this 3 by 18. This is no longer be this will no longer be 1 by 18, right? This will be less than 1 by 18, right? What would be the value of the modified count for this? We will basically discuss. Okay, so the Good-Turing probability says that things with 0 frequency, the probability of those things with 0 frequency is n1 by n, right? So in case of purple heron, as I mentioned, the maximum likelihood estimate says that this is 0, but the Good-Turing estimate says that this is 3 by 18. For the other cases, this is going to be the modified count. The modified count C star will be C plus 1 times NC plus 1 by NC. So let's say to estimate the case where C equals to 3, for example, I will look at C 3 plus 1 N4 by N3. To estimate the case for C equals to 2, I look at 2 plus 1 N3 by N2. Okay. Now let's look at the probability of woodpecker. So according to the maximum likelihood estimate, this was earlier 1 by 18. Now this is going to be C plus 1, 1 plus 1, C goes to 1 here, and N2 by N1, right? So 2 times 1 by 3, because N2 is 1, right? Look at here. N2 is 1. There is only one count 2, right? And what is N1? N1 is 3. So 2 times 1 by 3, 2 by 3. 2 by 3 is the modified count. What is the probability? 2 by 3 by 18, because the total bird that you have observed so far is 18. So the modified probability is 1 by 27. The earlier probability was 1 by 18, now this is 1 by 27. This is lower than the previous one. Right? Right? And I'm not going into the theoretical details of this. If you do the theory, if you do some maths is very easy. If you do the math, it will always guarantee that it will basically follow all the probability rules. Sum should be 1 and so on and so forth. Very simple idea. This is Good-Turing estimate. So these are the numbers before Good-Turing estimate. 0 count, 1 count, 2, 3, 4, 5, 6, 7, 8, and these are the modified count after Good-Turing estimate. So earlier it was 0, now this is some number, some non-negligible number, 0.0000270. Earlier it was 1, now this is 0.446. The count which was 2 earlier, now the count is 1.26. The count which was 3 earlier, now this is 2.24. Now look at the difference between these and advanced smoothing, the one that I discussed earlier. Right? Advanced smoothing, after advanced smoothing, we saw that the count, the modified count is very, very different from the original count, right? But if you look at here carefully, this is not very different. After Good-Turing estimate, the count is not very different from the previous one. But you still make sure that there is no 0. 0 is replaced by some number. Okay, now if you look at this thing very carefully, the numbers very carefully, although we did some tricks, but then if you look at the number very carefully, this is essentially the modified count is essentially the original count minus 0.75 roughly 0.75, right? The modified count is the original count minus roughly 0.75. Okay, if this is the case, then why can't we just discount an absolute number, let's say 0.75, from the bigram count, and let's see what happens. Okay, why do we need to do all these things? Ultimately, if it is only a discount of 0.75, so why do we need this math? We just discount some constant d from the count, and then we again modify the count. Okay, so this is called the absolute discounting interpolation. In the absolute discounting interpolation, what we do, so C of wi minus 1 wi by C of wi minus 1, this is the actual probability that we are interested in, right? Now I am saying that you discount some factor d from the bigram count, right? Because we observe that this is essentially 0.75. You discount some factor, right? And since this is some sort of interpolation, if you remember interpolation, back of interpolation I mentioned last class, interpolation is what? Let's say if we are looking at bigram probability, interpolation says that you basically come up with something which is a combination of bigram and unigram, right? Here also, now this corresponds to bigram and this corresponds to unigram. What is P of wi? P of wi is the probability, unigram probability of wi. What is wi? Wi is the second word in the bigram. Wi minus 1 wi, right? Unigram probability. And we can easily measure the unigram probability from the corpus. How? Let's say unigram probability of book, the word book. We look at all the occurrences of book and you divide it by the total number of tokens, right? And what is this lambda? Lambda is essentially again some sort of hyperparameter, whatever, right? That you can tune, right? Lambda can be a fixed value. Lambda can be a function of the unigram itself. In this case, in this particular formula, here lambda is a function of the unigram itself. And how do we measure this function? We have this held out set, validation set, and we run this thing multiple times and we decide the value of lambda. So, but this is not that easy, right? This is not that easy. The reason is, if you look at the unigram count, this P of wi, right? cases like stop words, right? A, I, so let's say pronouns, right? Articles, right? A, the, an, right? You see a lot of unigram counts, right? So therefore, for stop words, frequently occurring words, the unigram count will always be very high. Okay, so in the next uh, uh, method that we are going to discuss, Kneser-Ney or Kneser-Ney, there what we will see, instead of looking at or instead of measuring the unigram probability, we will measure something called a continuation probability of a unigram. We will measure the continuation probability of a unigram. What is the continuation probability of a unigram? We all understood what is an unigram probability, right? And you also understood the problems of unigram probability. Okay, now let's say there is a document which is related to the US, right, where the word Los Angeles, right, appears so many times, many times in the document, right? So then obviously the word Angeles, right, will have high frequency, high unigram count, right? So whenever you essentially sample some number, some word from the unigram distribution, it is highly likely that the word Angeles will be sampled, right? But in this continuation probability, what we will measure the number of unique bigrams. Please listen to this very carefully. Number of unique bigrams that this particular unigram completes. Number of unique bigrams that the given unigram which is under consideration completes. Okay, and what is the intuition again? Again, the intuition goes back to the Shannon's guessing game, right? Let's say if I ask you this sequence, my breakfast is incomplete without a cup of dash, right? Without a cup of dash. If you use a unigram count, unigram probability, you will see that the word Angeles has high probability than the word coffee. So, but if you sample Angeles here, if you add here, this is not going to be a correct answer, right? But if you look at it very carefully, the word Angeles, so the Angeles, so this word appears only with the word Los most of the times. So how many unique bigrams it completes? Only one. Whereas the word coffee appears with many other words: hot coffee, cold coffee, regular coffee, morning coffee, breakfast coffee, and so on and so forth. So instead of measuring the unigram count, we will measure something called the continuation probability of a unigram, right? Which says how likely is W to appear as a novel continuation, right? So we will look at all possible WXS, right? All possible WXS which is completed by the word W. So let's say W1, W, W2, W, W3, W, dot, right? W, N, W. So the novel continuation count of the unigram W is essentially N. Okay. So this is the continuation probability of a unigram. Look at the numerator very carefully, right? We are interested in all those bigrams Wi minus 1 W whose count is greater than 0, right? And how many such Wi's are there, mod of this set? So we are interested in all those Wi minus 1 such that count of this is greater than 0. So the cardinality of this set will be the numerator, will be the count of novel continuations. What is the denominator? What is the denominator? What do you think? What should be the denominator? Number of unique bigrams. Very good. Number of unique bigrams irrespective of the appearance of W. Right? So if you look at the denominator here, count of all the bigrams. So this is basically the set of all the bigrams whose count is greater than 0. Out of all the bigrams, how many unique bigrams are completed by the unigram W? Clear? If you do that, the probability of the word Angeles will be lower than the probability of the word coffee. Clear? So this is the idea of Kneser-Ney smoothing. Okay. So we replace the unigram probability by the continuation probability. Right? And here, if you look at the numerator, what is this? This says max of count minus D. So D is the absolute discount, right? Which was motivated by the previous one, 0.75. So the count minus this absolute discount D, comma 0, because it may happen that the number is negative. If the count is 0, then 0 minus, let's say D is 0.75, this will be negative. Should not be negative. So max of these two, right, by the count of unigram. Now can somebody tell me how to determine the value of this lambda? Let's say yeah, so in this particular formula, lambda is a function of Wi minus 1, right? Remember, this is a probability. Okay, I already discounted something from the first component. I discounted D from the first component, right? So how many discounts have happened so far for a particular Wi minus 1? Again, think of the bigram table. Okay, each row is basically Wi minus 1 and column is Wi, right? Bigram table, Wi minus 1 Wi. Now for every Wi minus 1, we need to make sure that the sum should be 1, right? Now tell me, if I discount minus D, if I discount D from the bigram count, we need to adjust somewhere. We need to adjust this so that the probability should be 1. Yeah. Think about it. Think about it. You are almost there. You are almost there. So for which entries this discount is applied? Now think about the row, right? There are some entries which are non-zero. There are some entries which are 0. So this D will only be applied to where? Non-zero, right? Non-zero and those whose value is greater than D. Greater than D, right? So I mean, this is again an approximate. I mean, this should be D, right? But again, assume that this is very small number. So for those cases whose count is greater than D, right, we will discount something from there, right? And what is going to be the numerator? Denominator? Numerator is D. What is the denominator? Count of? What is this count of Wi minus 1? Unigram count of previous word in terms of the table. Can you tell me in terms of the row? Huh? The count of basically the sum of values of the row, right? Yeah. Okay. So the numerator would be D times the mod of the set for which this condition is applied by the total count, because this part is discounted and this part is adjusted here. Okay, and if you do the math, you will see that this will always guarantee that this is 1. Okay, now most important part. So this was about smoothing. There are other smoothing techniques also, but generally we follow these three smoothing techniques: advanced smoothing, at-scale smoothing, Laplace smoothing, and Good-Turing and Kneser-Ney. The most important part here is how to evaluate a language model. Let's say you have come up with a language model which is a 5-gram language model. My language model is a 3-gram language model, right? How do you know that yours is better than my method? What do you think? What do you think? So the language model, right? When we evaluate a language model, there are two ways to evaluate a language model. One is called extrinsic evaluation. The other is intrinsic evaluation. What is extrinsic evaluation? Extrinsic evaluation is also called task-based evaluation. Okay, let's say this is a language model L1 and this is language model L2. I mentioned in the last lecture that we use this language model for downstream tasks. The task can be machine translation, task can be speech recognition, task can be spelling correction, right? Let's say you have the task machine translation, right, for which you apply a language model. You use a language model, and machine translation method model, let's say, is evaluated based on some matrix. Let's say the matrix is blue. Blue is a score that we generally use to evaluate the quality of a machine translation engine. Okay, so what we will do, I will feed the output of L1 to machine translation model and see the value of blue score. Similarly, I feed the value of output of L2 and see the score, right? And we will see which one is better. Okay, so I will feed the output of L1, I will feed the output of L2 separately in isolation, and we'll see for which language model the machine translation engine will perform better. And then I will say that, okay, let's say L2 is better than L1 or vice versa. This is a task-based evaluation. What are the problems in task-based evaluation? What do you think? Right. So if the quality of the machine translation model is not good, then you won't be able to essentially assess the actual performance of L1 and L2. What is the second problem? What is the second problem? The second problem is that it is not very clear which task we should choose. Right? There are plenty of tasks. There are thousands of tasks, right, where a language model can be applied. Right? Whether to choose machine translation or speech recognition system or what, right? It's not very clear. So what we do generally, we generally consider 10, 12 different tasks, and we see if a language model outperforms other language models across majority of the tasks, then we say that that language model is better. Okay. The third problem is that these extrinsic tasks, machine translation, speech recognition, they are time taking. They themselves are time taking because they, let's say they are neural models, right? So if you had to choose between L1 and L2, you will have you may need to wait for 7 days to see the performance of this downstream task, and then you have to decide which one is better. Let's say you don't have time, right? You have to choose very quickly among L1 and L2, right? You can't use this kind of models, this kind of frameworks, right? So we'll have to have some ways to intrinsically or implicitly measure the quality of a language model. Okay, so right, and for that what we use a metric called perplexity. Okay, again the motivation behind perplexity comes from the Shannon's guessing game, character guessing game, word guessing game. Okay, if I ask you this sentence, I always order pizza with cheese and dash, what would be the answer? Mushroom, maybe cheese and mushroom, or cheese with and what? Corn, right? Something like that, right? I mean, the set of vocabulary from where you choose the answer would be limited. Maybe 5 words or 10 words or 15 words, not more than that. But if I ask you, I wrote a dash, right? You see that the size of the vocabulary would be much longer. What does it mean? It means if I give you more context, then the language model should be able to predict things very easily. It is all about guessing game. Okay. So let me first define perplexity, and then I will tell you the intuition behind perplexity. Okay. So what is the definition of perplexity? The definition of perplexity is very simple. So let's assume that this is your test set W1, W2. In your test set, there are n tokens. You already have a training set, right? Based on the training set, you already you have already come up with the language model. You have already developed the language model. Let's say language model L1, language model L2, right? Now you are given a test set which consists of these tokens, sequence of sentences, right? Complete, incomplete sentences. What I do, I measure the probability of this sequence of sentences based on L1 separately and based on L2 separately. Right? Now, based on the probability, I will define this matrix called perplexity. What is perplexity? Perplexity is denoted by PP of a sequence of tokens 1 to n is 1 by nth root of P of W1, W2 ... Wn. This is same as P of W1, W2 ... Wn to the power minus 1 by n. Agreed? Agreed? What does it mean? If a language model produces high probability, right, the perplexity would be low. Okay? If it produces high probability, the perplexity would be low. Now, if a language model is a bigram language model, then this would be same as, how do you compute this one? If it is bigram language model, P of W1 times P of W2 given W1 times P of W3 given W2 ... P of Wn given Wn minus 1 whole to the power minus 1 by n. If it is unigram, then P of W1 times P of W2 ... P of Wn whole to the power minus 1 by n. Right? And we'll see that the language model which produces lower value, lower perplexity, will be considered as a better model. Now, why suddenly this metric? Why this 1 by n and nth root and so on, right? For the time being, forget about this nth, forget about this 1 by n, right? 1 by this 1 by this probability. And let's assume that this is simply P of W1, W2 ... Wn, right? To the power or nth root of this probability. So what is this? Nth root of this? This one is what? Geometric mean, right? This is geometric mean. The inverse geometric mean. We know the geometric mean, right? Arithmetic mean, geometric mean. Right? Now, why suddenly this? There's a very interesting connection between perplexity and entropy. Right? And we'll derive this thing here. Okay. So, we all know what is entropy. So entropy, let's say there is an event X, right? Entropy of this is announced entropy. Okay, entropy of this event X. Let's say there are n number of outcomes, right? and each outcome has certain probability, right? So this is essentially sum of pi or whatever pxi log of pxi minus, okay. And what is this xi? Xi is one outcome of x, right? There are n number of such outcomes, okay. Now if the outcome is uniform, right, let's say there are n trials, and let's say there are c possible outcomes, and each outcome appears equal number of times, c by n or n by c, right? Versus if the outcome is biased, whose entropy would be high? Entropy is a measure of randomness, right? Whose entropy would be high? Uniform, right? We all know this famous plot, right? This is P and this is H. When the probability is same for all the outcomes, the entropy is maximum, right? All right. So we all know entropy. Now we will now for a sentence, for a language, specifically for a language. A language is a language essentially is denoted by a sentence, right, or a sequence of tokens, right? So how do we measure the entropy of a sequence of tokens? Now remember this. Here there is a random variable which indicates the outcome of an event. Now here, what is the random variable? A random variable indicates a sequence of words, right? And how do you measure this entropy here? This is same as minus of, right, sum of, let's say, p of w1 w2 wn, right, log of p of right, and this is for all such sequence of words which belongs to the language L, isn't it? You all agree with this equation, right? Now what we define entropy rate. Why we define entropy rate? Because this is an entropy of a sequence. We need to define an entropy of a word, of a token, right? So we define something called entropy rate or per word entropy, right? What is entropy rate or per word entropy? This is basically 1 by n of this h. Why? Because there are n words. This is the total entropy. Per word entropy is 1 by n of this. Simple, right? So this will be minus 1 by n summation of p log p. Okay, this is entropy rate. Now think about it. I am only considering those cases, those sentences or those sequences whose length is n, right? But in a language, in a document, there are sentences, there are sequences of multiple size, right? Some sequences will be will have length of 5, some will have length of 6, some have 10, and so on and so forth, right? But here we are only considering those sequences whose length is n, right? So how do we generalize it? We generalize it using this limit theory, right? We say that limit n tends to infinity, right, 1 by n p of this log p of this. Okay, so remember here language is a stochastic process, right? Language is a stochastic process. What's the stochastic process? It generates tokens. So language generates tokens based on some distribution, right? And the distribution is something which we do not know. And P is a distribution that we do not know. Okay. Okay. So this is the entropy rate. Okay, and we denote this entropy rate by H of L. Now H of L is this one. So far so good. Now we will apply a theorem. Again, I will not go into details of the theorem. This is called the Shannon-Macmillan Breman theorem. Okay. The Shannon-Macmillan Breman theorem says if the stochastic process is regular, what is the regular stochastic process? It should be stationary and ergodic. Again, I will not go into details of this, right? If a process is a regular process, right, I can approximate this. I don't need I don't need a lot of sentences, right? I need a sentence whose length is significantly large. I don't need to basically take the sum over all sentences. I can approximate it by a sentence whose length is significantly large, meaning it can be approximated to limit n tends to infinity log of, right, log of w1 w2 dot wn, and again this p is also here. What I did, I just removed the summation. I only removed the summation because the summation says that let us consider all the sentences, right, of different length and so on and so forth. Now using this theorem, I said no, I will not consider all the sentences. I'll consider only that sentence, only one sentence whose length is significantly long. Okay, and I will, this is minus. Okay, and I will also assume that the probability of this sentence is 1 by n. Okay, now these are, now if you are not convinced by this, I strongly suggest that you go through this theorem and you understand. It's a very standard theorem in information science, information theory. Okay, so this boils down to limit n tends to infinity 1 by n log of w1 w2 wn. Huh? P. Yes, P. Sorry, P. Of course, P. Okay. Now I define another concept, cross entropy. Entropy we know. This is entropy. What is cross entropy? What is cross entropy? When do we need cross entropy? Let's say there are two events. There are two random variables indicating two different events, right? And let's say you want to measure the closeness or difference or some sort of similarity between two events, right? Whether one event is independent of other events and so on and so forth. In language, nobody knows what is the actual probability or the gold probability of generating a word. Nobody knows. If you knew what is the gold probability of generating a language, then you would have solved the language generation problem. Nobody knows how a language is generated, right? We approximate this process using language model. We says that look, we will design a language model which will try to mimic the way language is generated. You get my point, right? So we will define something called cross entropy here. Cross entropy between the actual way a language is generated L and our model M. Okay, and what is the cross entropy formula? Sum of P of PL of, let's say, xi, right, log of PM of xi, right? What is PL? PL is the probability obtained from the language itself, assuming that we know the oracle, we have access to the oracle, whereas PM is the probability obtained from the model. Let's say the model is a bigram model or trigram model, and this is cross entropy, right? Again, if you apply this Shannon-Macmillan-Brayman theorem, you can approximate this. Again, I mean, from here we will consider entropy rate or per word entropy, right? 1 by n, then limit, and so on and so forth. Right? Apply all these things, all the tricks that we applied here. So if we apply this formula, if we apply the theorem again, this theorem says that the cross entropy can be written as limit n tends to infinity minus 1 by n log of Pm. I mean, in our case, xi is essentially what? W1, W2, dot, 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 Wn. Okay? So cross entropy has a very nice property, by the way. Do you know the cross entropy has a bound? The original entropy H of P is the lower bound of the cross entropy P of H of, let's say, or L. And you can prove this very easily. Can you prove this? Can you prove this theorem? Can you prove this theorem? H of L is bounded by H of L comma M. What is L? L is the true the oracle language, right? Event. Or M, and what is M? M is the model, right? Can you prove this? What is H of L? H of L is, let's say, minus, right, log of Pi, right? If you replace Pi by Mi times Mi, right? So minus Pi log of Mi minus, right, Pi log of Pi by Mi. What is this? This is cross entropy. This is H L M. And what is this, by the way? Pi log Pi Mi. Let's see. What is this? This is scale divergence. This is scale divergence between Pi and Mi, P and M, right? So H of L is essentially H of L M minus scale divergence of L and M. So it means that H of L is less than equals to this. Now let's try to understand, at least intuitively try to understand this equation, right? What it says? It says that the entropy, what is H of L? H of L is the entropy of the true event L, which you do not know. Language, right? What is H L comma N? Is the cross entropy between the language and the model. And what is the scale divergence? Scale divergence is the difference between L and M, right? So if you reduce the difference between language and the language model will come closer to the language. All right. So we have seen what is okay. So just forget about all the theories. Okay. Just focus on this part. Just focus on maybe this part. Okay. Okay. And again, to simplify this, you ignore the limit, because when you consider only one sentence whose length is infinite, we can ignore the limit also. right? Only this part is there, 1 by 1 minus 1 by n log of p, right? Now my claim is perplexity pp is 2 to the power entropy. This is my claim. Okay, now let's see. We know the formula of perplexity already. We have seen the formula of perplexity. Now what is this h? H we have seen. This is minus 1 by n log of p of w1 w2 dot 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 wn, right? So you move this to the power of probability, okay? Then this log and 2 will vanish because it's the power of 2, base is 2. So this is going to be p of w1 w2 dot dot wn to the power minus 1 by n, right? Now pause and ponder, think about it. What is entropy? Entropy, intuitively entropy says the average number of bits required to encode an information, right? Log of what is log of 1 by pi? What is minus log of pi? What is minus log of pi? Number of bits required, minimum number of bits required to encode. Pi log of pi is what? P minus pi log of pi is what? Expected number of bits required, because pi is essentially the probability of that outcome, right? So entropy says that what is the expected number of bits required to encode an information. Number of bits. What is 2 to the power number of bits indicating? Let's say the number of bits is 3. What is 2 to the power 3? Number of possible cases, number of possible words that you can generate with 3 bits, right? So entropy says then what this, so the perplexity is what is the number of possible words that you can generate. Okay, now assume that you have a sequence of tokens and you want to estimate what is going to be the next word. If a language model's entropy is high, if the language model's entropy is high, so 2 to the power that will also be very high. That means there are lots of possible candidates that can come there. If a language model's entropy is low, that means your possible set of words is also low. That means you are more uncertain, you are more certain about the next token. Clear? Okay. So someone can say that why do we need perplexity? I can use entropy. I can use entropy as a measure for evaluation. But entropy and perplexity are proportional, right? If I use entropy as a measure for evaluation, it doesn't make much sense. Intuitively, if I say that okay, the average number of bits is 3 for this language model, what does it mean? Versus if I say that for this language model, this language model can generate 8 possible tokens for the next word, versus this language model can generate 3 possible tokens for the next word. This makes more sense. You can say that okay, next the second language model is better than the first language model because the second language model is more certain. Clear? So this is the beauty of perplexity. Let's look at some of the problems of statistical language model. We discussed n-gram models, we discussed smoothing techniques, we discussed evaluation measures, right? So n-gram models, the major problem is this fixed window size, because I have to choose the window and based on that I have to measure the count and so on. What would be the size of the window is not very clear. The second problem is that as the number of bigrams increases, this matrix size will increase, right? Even if you do a lot of smoothing, you will still see that there are lots of small values, zero counts and so on and so forth. It is very bad in handling out of vocabulary words, OOV. I mentioned one technique last day, but that technique is also not that great given the the amount of new words coming in every day, right? And of course it is computationally very expensive to create or to come up with this kind of n-gram this bigram table. bigram or trigram table, assuming that you have a trillion size corpus, right? So what is needed? We need some sort of better understanding of some sort of representation which understands the context properly, right? We will also look at how we make the entire thing scalable, and so on and so forth. Thank you.